Hello and welcome to SyncThoughts. SyncThoughts is an educational series of videos on timing concepts and technologies featuring me, Jim Olson, Solutions Architect from Microchip Frequency and Time Systems. Today's educational video topic is setting, holding, and maintaining time. So put on your timing hats and let's get started. Setting time, or UTC traceable time, can be done two ways. One, we can use a local timing receiver at the endpoint application where the timing is consumed. Or two, we can send timing to the endpoints over the network. If we have many endpoints, it can be very expensive to use timing receivers at endpoint locations. So in most applications and use cases, it's much more cost-effective and practical to use network-based timing services. If we want high accuracy time transfer, we use PTP-based network time transfer technologies. When we transfer accurate UTC traceable time, there's three components for time error. The first is the source clock. The closer the source clock tracks to UTC, the more we can allocate the error budget for time transfer to the network itself. So time error reduction within the source clock itself is an important concept related to time transfer. In the telecom world, with ITU standards, we have the concept of a primary reference time clock that tracks within 100 nanoseconds to UTC traceable time. We can also go up the ladder a little bit for higher accuracy with the PRTC using what's called a PRTC-B, which tracks even closer to UTC time within 40 nanoseconds. There's also an ITU standard called an enhanced primary reference time clock that uses both timing receivers and cesium atomic clock technologies to produce high accuracy, and when tracking GPS or GNSS, we can track within 30 nanoseconds to UTC. So the source clock does contribute some level of time error. The less the better, so we can allocate more time error to the network itself. In the network, time error reduction can be accomplished using many different types of technologies. There's boundary clock technology, which is associated with what we call on-path support. There is transparent clock technologies, which is more of a software-based way of mitigating time error within devices. Or we can do technologies for time transfer like two-way time transfer over optical fiber cables that can do very, very high accuracy, where we can calibrate out delays that don't change or that are known delays that are static. The third thing that introduces time error is the endpoint client itself. How much time error is consumed in the total time error budget allocation by the endpoint device depends on the design of that device and the technologies associated with the endpoint application that is consuming the timing services. When it comes to time transfer protocols or technologies, if we do not have highly stringent accuracy requirements, we use what is called Network Time Protocol, or NTP servers. NTP servers can deliver accuracy in the microseconds or millisecond range of accuracy, but if we need single-digit microsecond accuracy or nanoseconds of accuracy, we use PTP, or Precision Time Protocol, for these types of use cases. The main concept on time transfer is fairly simple. If we have a receiver, for example, that uses GPS as a UTC traceable source, and that receiver tracks 1 microsecond from UTC, we can send a timestamp from that receiver at point A to an endpoint in the network that's consuming the time services at point B. And if the delay of the network is 100 microseconds, we can deliver an accuracy of 101 microseconds to that point B endpoint. But let's say that's unacceptable and we want to deliver higher accuracy. We have to have some way to deal with network delay. So what we do is we bring the problem down not from network delay to just asymmetrical delay. When we use PTP for time transfer, for example, if we have 2 microseconds of asymmetry between point A and B, we can get down to 1 microsecond of time error to point B. So how does this work using the PTP protocol? If I send a timestamp from the receiver or the grandmaster to a PTP client at point B, when that client receives the timestamp, he's going to turn around and send it back to the grandmaster, asking the grandmaster, say, hey, what is the total delay or the round trip delay from A to B, back from B to A, and then please send me another timestamp to correct for that error. So when the grandmaster receives this, and since it has GPS, it can calculate very accurately the round trip delay. Let's say the round trip delay total is 10 microseconds. So we assume that it's 5 microseconds in the forward direction and 5 microseconds in the reverse direction. But all networks are not symmetrical, where the forward and reverse delay are always the same. They are asymmetrical to some degree. So let's say the real delay in the forward direction is 6 microseconds. In the reverse direction, it's 4 microsecond delay, which is 10 microseconds of time transfer error. Since we don't know what the asymmetry is, we're assuming it's 5 microseconds in each direction, we're going to send a 5 microsecond correction to the client with the next timestamp that we send to point B. But if we see that asymmetrical error, where the delay is actually 4 or 6 microseconds in the forward or reverse direction, that's 2 microseconds of asymmetry that will produce a 1 microsecond time transfer error. So there's limitations to PTP where whatever we can get the asymmetry down to, we can correct to half of that. So that's how the PTP protocol works, and we can improve the performance by eliminating some time error in the network, by eliminating the time error or asymmetrical time error of some of the devices in the path between the receiver grandmaster function and the client itself. We can use technologies such as boundary clocks, transparent clocks, QoS DSCP markings if we use layer 3 unicast PTP profiles. We can also use what's called synchronous Ethernet when we use boundary clock technologies to improve the performance of the boundary clocks. So boundary clocks are what is called on-path support, which mitigates time error in a switch or a router. We can use transparent clocks, which also mitigates time error in switches and routers by measuring the delay of the PTP packets when they traverse switches and routers and notifying the client at the endpoint of what those delays are. So we can use both layer 2 multicast and layer 3 unicast PTP profiles with various mitigation of time error in switches and routers. Synchronous Ethernet is important when we use on-path support because it does improve the performance of the boundary clocks themselves. Even though synchronous Ethernet is not a time transfer technology, it is a frequency reconstruction concept or technology. Next up, we're going to cover the concepts of maintaining time and holding time, or what we refer to as holdover. So maintaining time and holdover are not the same thing, and we can use technologies to maintain time. So maintaining means we are not going to drift away from our reference that we have established, such as UTC traceable source clock reference. In this case, we're not going to drift, meaning we are not going to move away from UTC if we lose our reference. We're going to maintain that UTC accuracy. We can do this with a concept called assisted partial timing support, which is an ITU standard G.8273.4. APTS, or assisted partial timing support, creates what we call a GNSS or GPS proxy when GPS is compromised. So if we have a receiver at point A and we have another receiver at point B in the network, we can establish a PTP flow from point A to B between the two receivers. The APTS technology allows us, if the receiver at point B loses its reference from GNSS or GPS, we can maintain UTC traceability at point B by using asymmetry calibration techniques on PTP flows between those two devices. If we have GPS reference operating at point A and GPS reference operating at point B, we can measure the exact delay in the forward direction of the PTP flow and back in the reverse direction from point B to point A and know exactly what those delays are. If we know the exact forward and reverse delay, we know what the asymmetry is between point A and point B. So once we have measured and calibrated that, if we lose our reference at point B, we can continue to make the corrections we need on the PTP timestamps for the asymmetry that exists between point A and B to maintain UTC traceable time or create a GPS or GNSS proxy function at point B in the network. There are many improvements coming to the APTS technology and algorithms from Microchip FTS to get even better accuracy for APTS applications. But APTS is a fabulous technology to maintain UTC traceable time and address what we call GPS or GNSS vulnerabilities for failures, as well as things like jamming and spoofing events that occur sometimes in different geographical spots around the globe. The next concept is holdover. When a GNSS or alternate reference, like a cesium reference, is lost, connected to a receiver, we are going to go into holdover. How fast we drift off in frequency or time from UTC depends on the quality of the oscillator we have in that receiver. The system will drift based on the quality of what we call the holdover oscillator. There's different levels of quality for holdover clocks or oscillators. A crystal oscillator is the lowest quality of holdover oscillator that drifts fairly fast, where we can achieve microseconds of error in 24 hours. We can put rubidium oscillators or rubidium atomic clock oscillators for holdover oscillators in receivers that are much better than the crystals, where we only have nanoseconds of error accumulation once a reference is lost over 24 hours. Or we can put a system together where our enhanced holdover component is not inside the receiver, but outside the receiver in a cesium atomic clock package. We connect a cesium and we use EPRTC or enhanced primary reference time clock algorithms in the receiver, and we lose the reference to the receiver from the GPS or GNSS connection. We can provide enhanced holdover that is phenomenal, where we can hold a few nanoseconds for several days or even weeks. And we can achieve incredible performance where we can hold less than 100 nanoseconds for 30 or 40 days or even more. So holdover components are important to understand based on what your requirements are. If the receiver you're using is in the world of milliseconds or microseconds, crystal oscillators are good enough holdover. But if your applications are down in the low microsecond or nanosecond range, that's when we have to consider better holdover oscillators like rubidium atomic clocks. And in many cases for high accuracy where not just accuracy, but reliability and resiliency is very important, we would use things like enhanced primary reference time clock systems. So to summarize what we have covered in this video for timing concepts, we start with setting time. So high accuracy requires time error mitigation, some level of on-pass support, boundary clock functions, or using dedicated fiber. Or in some cases, if we're running layer 3 unicast PTP, we use QoS markings. So high accuracy means we have to do some level of engineering of the timing services to achieve high accuracy time transfer. The source clock also plays an important piece in time transfer accuracy. The better our source clock tracks to UTC, the more time error we can allocate to the network itself. So things like ePRTCs or PRTCBs that track closer to UTC is one way to help us meet our error budget to the endpoints when we're using extremely high accuracy applications or requirements. Maintaining time means we're going to try to create a GPS or GNSS proxy to address GPS or GNSS vulnerability issues. So maintaining time with APTS or assisted partial timing support means no holdover. We are not going to drift away from UTC when we use APTS. So we're not technically in a holdover condition if we lose our GPS or GNSS reference at point B in the network. So this is an important point because if we use APTS and no holdover means the chances of going into holdover are very slim or none. So we can use low-cost oscillators in our receivers at all of our point B locations in the network that are being backed up from location A using APTS. So it's a very cost-effective way to address GPS or GNSS vulnerabilities. It works with no full on-pass support. It's a layer 3 unicast model, and it does automatic asymmetry calibration. And with the Microchip FTS technology, we can capture and log different asymmetry profiles. So if we are in the APTS mode of operation and we lose GPS or GNSS at our point B location, if the network rearrangements occur that cause asymmetry profile changes and we have captured that profile previously, we will switch to that profile and there will be no degradation in the timing accuracy or drift from UTC. The last thing we talked about was holdover. So if we have an application or use cases where our holdover requirements are in the millisecond range or microseconds or high levels of microseconds, we use crystal oscillators for holdover. But if we have single-digit microsecond or nanoseconds of accuracy in our holdover requirements, we use rubidium atomic clock oscillators for holdover. But if we want something really good, super accurate holdover, where we need reliability, where we need weeks or months where we don't drift too far off from UTC, we can use the enhanced primary reference time clock or ePRTC holdover systems, where the holdover component or oscillator is not inside the receiver, it is outside the receiver in a package that's called the cesium atomic clock package. So cesium atomic clocks with ePRTC algorithms mean super enhanced holdover where we can hold 100 nanoseconds for more than a month. So it's exponentially better than not just a cesium itself when we use ePRTC algorithms, but it's exponentially better than rubidium atomic clocks by a factor of maybe 100 times better. So these technologies are available, and when we engineer our timing for our networks, when we use network-based timing services, these concepts of setting time, maintaining time, and holdover are important to understand when we go through our engineering exercises. So that ends our educational video for today on timing concepts and technologies. Thank you for attending, and I hope you can attend some of my other educational videos because this is part of a series. So thank you for attending. See you later. Just remember, timing is everything.